Tropical cyclones. Tropical cyclones are powerful weather systems that develop over warm tropical and subtropical oceans. They are associated with extremely low air pressure, meaning that air at the Earth's surface is rising rather than sinking. As air rises, pressure at the surface decreases, which helps draw in surrounding air and fuels storm development. Tropical cyclones are sometimes referred to as tropical storms, hurricanes, or typhoons depending on where they form, but they are all the same type of atmospheric phenomenon. Tropical cyclones gain their energy from warm ocean water, which provides heat and moisture. As the storm strengthens, surface winds begin to rotate around the center in a continuous circular pattern known as closed circulation. The direction of this rotation depends on the hemisphere. Storms rotate anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere due to the Coriolis effect, which is caused by the Earth's rotation. As wind speeds increase, a distinct structure begins to form. One of the most recognizable features of a tropical cyclone is the eye, a calm and relatively clear area at the center of the storm. Surrounding the eye is the eye wall, a ring of towering cumulonimbus clouds where the strongest winds, heaviest rainfall, and most intense weather conditions are found. How do tropical cyclones form? Tropical cyclones typically form between 5 degrees and 30 degrees north and south of the equator. They cannot form directly over the equator because the Coriolis effect is too weak to cause rotation. One of the most important conditions for cyclone formation is warm sea surface temperatures of at least 26.5 degrees Celsius, extending to a depth of around 50 to 60 meters. When the sun heats the ocean, the air above the warm water also heats up and becomes less dense. This warm, moist air rises, creating an area of low pressure at the surface. As the air rises, it cools and condenses to form clouds and heavy rainfall. Condensation releases latent heat, which provides additional energy to the storm and causes further uplift. This positive feedback process allows the storm to intensify. Air from surrounding areas is drawn in to replace the rising air. Because of the Earth's rotation, this incoming air begins to spiral, forming the rotating wind pattern characteristic of tropical cyclones. As long as the storm remains over warm water and vertical wind shear is low, it can continue to strengthen. Once the system moves over land or cooler water, it loses its energy source and quickly weakens. For a tropical disturbance to develop into a tropical cyclone, several key conditions must be met. Warm ocean water of at least 27 degrees Celsius, an unstable atmosphere where temperature decreases rapidly with height, high levels of moisture in the mid-troposphere, sufficient distance from the equator to allow rotation, usually at least 200 to 300 kilometers, low vertical wind shear, meaning little change in wind speed or direction with height. Together, these conditions allow a warm core, non-frontal cyclone with deep convection and a closed surface wind circulation to develop. Structure of a tropical cyclone. A fully developed storm has a well-defined structure. At the center is the eye, typically 30 to 50 kilometers wide. The eye is an area of descending air, light winds, and relatively clear skies. Despite the extreme weather surrounding it, conditions in the eye can be calm. Surrounding the eye is the eye wall, a ring of towering cumulonimbus clouds where the strongest winds, heaviest rainfall, and most intense weather conditions are found. Classification of tropical cyclones. Tropical cyclones are classified according to their maximum sustained wind speeds. Tropical depression, winds below 39 miles per hour, 63 kilometers per hour. Tropical storm, winds between 39 and 73 miles per hour, 63 to 118 kilometers per hour. Hurricane or typhoon, winds of 74 miles per hour, 119 kilometers per hour, or higher. Hurricanes are further divided into 5 categories using the Saffir-Simpson hurricane wind scale. Categories 3 to 5 storms are known as major hurricanes and have wind speeds of at least 111 miles per hour, 178 kilometers per hour. While wind speed is important, it is not the only factor determining damage. Rainfall, storm surge, and the vulnerability of affected areas all influence the overall impact. Naming tropical cyclones. The terms hurricane, typhoon, and cyclone all describe the same storm, but are used in different regions. Hurricanes, Atlantic Ocean and Eastern Pacific; typhoons, Western Pacific; cyclones, Indian Ocean and parts of Southeast Asia. Once a storm reaches tropical storm strength, it is given a name chosen by the World Meteorological Organization, WMO. Names are reused every 6 years, but particularly destructive or deadly storms have their names retired to avoid confusion and out of respect for victims. Hazards associated with tropical cyclones. Tropical cyclones pose several serious hazards, including strong winds, heavy rainfall, storm surge, tornadoes, and coastal flooding. Although high winds receive the most attention, water-related hazards are the leading cause of death. Extreme rainfall and flooding. Warm air can hold large amounts of moisture, and tropical cyclones contain exceptionally warm, humid air. As this air rises and cools, it produces intense rainfall that can last for days. Flooding often occurs far inland, long after the storm has made landfall, particularly in river basins and low-lying areas. Storm surge, the greatest threat. Storm surge is the abnormal rise in sea level caused by strong onshore winds pushing water towards the coast. This can lead to rapid and severe coastal flooding. Even relatively weak tropical storms can produce dangerous storm surges, and the size of the surge does not always match the storm's category. Just 15 centimeters of fast-moving water can knock over an adult, while 60 centimeters can carry away vehicles. Category 5 storms can generate storm surges over 6 meters high. The highest recorded storm surge, approximately 12.8 meters, occurred in Australia in 1899. Predicting tropical cyclones. Modern forecasting relies on advanced global weather models, such as the ECMWF, GFS, and UK Met Office models. These models analyze atmospheric conditions, sea surface temperatures, and wind patterns to predict storm formation, intensity, and track. While track forecasts have improved significantly, predicting changes in storm intensity remains more challenging. Reducing the impacts of tropical cyclones. There are several strategies for reducing loss of life and damage. Forecasting and warnings, improved satellite monitoring and modeling allow earlier warnings and evacuations. Coastal management, maintaining beaches, dunes, and wetlands helps absorb storm surge energy. Engineering solutions, seawalls, flood barriers, and surge gates can protect vulnerable cities. Building regulations, stronger building codes reduce wind and flood damage. Land use planning, limiting development in high-risk coastal areas reduces exposure. Evacuation remains the most effective way to protect human life, especially in low-lying coastal regions. Case study: Hurricane Katrina, 2005. Hurricane Katrina was one of the most destructive tropical cyclones in U.S. history. It caused over 1,800 deaths and approximately $125 billion in damage, primarily in New Orleans and surrounding areas. Katrina reached Category 5 strength over the Gulf of Mexico before weakening to Category 3 at landfall. The majority of deaths were caused by flooding following the failure of levees designed to protect New Orleans. Around 80% of the city was flooded, leaving thousands stranded without access to food, clean water, or medical care. Investigations later identified serious design and maintenance failures in the flood defense system. Katrina highlighted the importance of effective disaster planning, reliable infrastructure, and clear communication between authorities and the public. Tropical cyclones and climate change. According to the IPCC Sixth Assessment Report, AR6, human-induced climate change is already influencing tropical cyclones. While the total number of storms globally may not increase significantly, several key changes are expected. Sea level rise is very likely to increase coastal flooding during storms. Tropical cyclone rainfall rates are likely to increase by around 10 to 15% for every 2 degrees of global warming. The proportion of very intense, Category 4 and 5 storms is likely to increase. Storms may intensify more rapidly, reducing preparation time. Overall, climate change is expected to make tropical cyclones more dangerous due to heavier rainfall, higher storm surges, and stronger peak intensities, even if storm frequency remains similar. Key terms to learn and use in exams. Tropical cyclone, a rotating low-pressure storm system forming over warm tropical oceans. Low pressure, an area where air is rising, leading to cloud formation and rainfall. Latent heat, heat released when water vapor condenses, powering tropical cyclones. Coriolis effect, the deflection of winds due to Earth's rotation. Closed circulation, continuous circular wind flow around a storm center. Calm, clear center of a tropical cyclone with descending air. Eyewall, ring of intense thunderstorms surrounding the eye. Storm surge, abnormal rise in sea level caused by cyclone winds. Vertical wind shear, change in wind speed or direction with height. Saffir-Simpson scale, classification system based on maximum sustained wind speed. Rapid intensification, a sudden increase in cyclone wind speed over a short time. Mitigation, long-term actions to reduce hazard risk. Adaptation, adjustments to reduce vulnerability to hazards. Resilience, ability of a community to recover after a hazard event. Thank you for listening to this Geography Expert podcast. You can find access to all Richie's free resources through his website, www.richiecunningham.com, including links to his Geography Expert Substack and podcasts.